So now how about our quantum skateboarder or quantum snowboarder? Well, from the point of view of the Schrodinger equation, we have minus h bar squared over twice the mass times the second derivative of the wave function plus that potential energy function times the wave function. That's our half pipe, has got to be equal to the total energy times the wave function. That's Schrodinger's equation in one dimension. So that is, we can move the potential times the wave function over to the right and rewrite that as the second derivative of the wave function times h bar squared divided by twice the mass, change the sign, is equal to the energy minus the potential energy, all times the wave function. So minus h bar squared over twice mass divided by that wave function now, times the second derivative of the wave function, is equal to the difference in the total energy and the potential energy. Well, that is the kinetic energy. So that means that the second derivative of the wave function divided by the wave function, we can also call that psi double prime over psi, that is the relative amount of curvature, and I'm going to call that the curviness in this class. Curviness is not a term that you'll encounter in any other classical text, but I think it's a good way of thinking about it and describing it. So we call that, the second derivative divided by the function, we'll call that the curviness. So one way to re-describe the Schrodinger equation is that Schrodinger says that the curviness of the wave function tells us how much kinetic energy an object has. And let's see. Schrodinger was German, so that would be about die Kurvigkeit, not quite a word in German, der Wellenfunktion. Erzählt uns, wie viel kinetische Energie hat es. So let's keep thinking about this curviness thing again. So just what exactly is it? Well, as we defined it before, curviness, as we call it, is the curvature, the second derivative of any function, which is how much it bends, divided by the actual size of the function at any point. So basically, here's a curve that bends really a lot. So that's a function that has relatively high curviness compared to a function over here that I'll say has fairly low curviness. And as drawn, these two both have about the same amplitude. They have about the same height, but one is about accomplishes the same business going from baseline to top to baseline again, and maybe a fifth the total distance. So its curviness would be 5 times greater. Now, especially because the wave function is normalized, because when we square it and integrate it up over all space, the result has to be 1, because the probability of finding the object somewhere has to be exactly 1. Really, the only way for a function to achieve high curviness, which means high kinetic energy, is to go back and forth across 0 many, many times. It basically has to stay someplace close to 0, because when you integrate it all up, it's got to be 1. So a function with a very high curviness, if here's a baseline, is going to look like this. It's going to go up and down and up and down and up and down and up and down and up and down, and it's going to cross 0 again and again and again and again and again, as indicated by those red circles. So those 0 crossings mean the wave function has lots of nodes, and it's got lots of energy. Now, the overall sign of this is super important, especially that minus sign out on the beginning of the term minus h bar squared over twice mass times the second derivative. That minus sign there really has everything to do with how this system behaves. So let's kind of think this through just very simplistically here, but it's all you really need to know. So this total curviness, as we call it, with all these signs, is equal to the kinetic energy. Energy minus the total energy minus the potential is equal to the kinetic energy. So let's have some x-axis here, some baseline, and that line's at x equals 0. And over here on the left, let's imagine that the wave function is greater than 0, but it's bending down. It's a frowny face, which means the second derivative is is less than 0. So the function itself, which we're dividing by there, that's greater than 0 here. But the frowny face, the second derivative now, is less than 0. So that's a minus sign. And then that minus sign out in front of everything, well, that's a minus sign, of course. And so what we're left with is a minus sign times a positive sign times a minus sign. A negative times a positive times a negative. That's a double negative. And overall, that winds up as positive. Now, on the other hand, let's imagine the function over here toward the right, where the function is less than 0, so that's a negative. But now we have a smiley face. We have upward curvature, upward second derivative, so that's a positive. And once again, that minus sign over there is a negative. And so this time we have a negative times a positive. Once again, we have two negatives, and the overall term is greater than 0. So in each case, with the wave function above 0 and the wave function below 0, the second derivative cancels out the sign appropriately, and we wind up with an overall function, the overall term from the operators that is greater than 0. So what that means is if the kinetic energy, which remember is the right-hand side of the equation, if that is positive, and a positive kinetic energy seems like a very obviously reasonable thing, like many things in quantum mechanics, that's going to come into question later, but so far that seems reasonable. Then, the way the Schrodinger equation works out, the curvature has the opposite sign of the function. So when the function is above 0, the curvature is negative. When the function is below 0, the curvature is positive. And that is something that we would call a restoring function. It tends to bend the function back towards 0. And that's the very description of a wave-type function. It's always bending itself, restoring itself back toward the 0 point. And so again, because of all that bending, if the function has high kinetic energy and high curviness, then it's going to cross 0 many, many times, and you're going to have lots of nodes being related to having lots of kinetic energy. So here's a function again. Here's 0, and a function with high kinetic energy crosses 0 many, many times, again and again and again and again, and that corresponds to a lot of nodes. And now remember that when you think back to atomic orbitals, orbitals with lots of nodes tend to be high energy, maybe a d orbital from inorganic chemistry or whatever. Those are the high energy nodes. And that's going to turn out to be exactly the same thing. Those orbitals are in fact wave functions of the electron. So in summary, what we've learned about here in the Schrodinger equation is this thing called the Hamiltonian operator, that H with the hat on top of it. And what Schrodinger tells us, that this Hamiltonian operator is this expression minus h bar squared over twice the mass times the second derivative, and that's related to the kinetic energy, then plus the potential energy. So the Schrodinger equation is fundamentally an expression of conservation of energy. Now that term minus h bar squared over twice the mass, I've been saying second derivative, but it's always so far in this one-dimensional case been written as d squared over dx squared. But in math in general, we have another term called del squared or nabla squared. So I can write this as minus h bar squared over twice mass, and then this upside down triangle, del squared. And that's just a way to say, and then plus the potential, of course. That del squared is an indication that basically says in mathematics, just take the second derivative. However you want to do it, whatever coordinate system you happen to be in, just go and get the second derivative in the appropriate coordinate system, and that's going to be the answer that we need. So that, again, that's a bit of abstraction that we'll use later on, but basically it's sometimes these second derivative expressions can get kind of complicated, but don't panic. The del squared just says go ahead, go into the right units, go into the right coordinate system, and then figure out the second derivative as necessary.